All right, on Monday we were talking about the types of reactions to prepare aldehydes and ketones from alcohols. You have primary alcohol can oxidize into an aldehyde. A secondary alcohol can oxidize into a ketone. Tertiary alcohol does not oxidize, no reaction, right? Okay, so in that process you will remove two hydrogens and you will form the double bond. So to form a double bond you have to remove hydrogens, which is also a process of removing electrons. That's why they call it an oxidation process, because oxidation is loss of electrons. Okay, if your oil rig means oxidation is loss, that means you got to lose hydrogens. Reduction is gain. You got to gain hydrogens back to reduce something. Okay? All right, so primary alcohol oxidation. Here you see that I have the OH attached to a carbon that only has one other carbon attached to it, right here, this one. That makes it a primary alcohol. So because it's a terminal OH, that means when you oxidize it, and this symbol right here for oxidation does not represent oxygen. It represents an oxidizing agent, like potassium permanganate or things of that nature. Okay, so it represents a class of molecules, not just O2 or oxygen. It doesn't represent oxygen. Okay, all right. So you can see that this hydrogen and this hydrogen are going to be removed. And in the process of doing that, you're going to form a double bond. And you will then have an aldehyde. Okay? It's an aldehyde because it's a terminal carboxyl group. Okay, here's another example. This is not a primary carbon. Count the number of carbons attached to it. It has two other carbons attached to it. So that means it is a secondary carbon, which makes this a secondary alcohol. Okay, so this is a secondary alcohol. Secondary alcohols, when they oxidize, so here's oxidation. When they oxidize, we are going to remove the hydrogens, and then we are going to form a double bond between the carbon and the oxygen. And you will get a ketone in this case. Ketones are where the carboxyl carbon is embedded inside of the carbon chain instead of at the terminal end. Okay, so it is embedded in that carbon chain. It makes it a ketone in that case. Okay. We're not showing it, but you could, it's over here. It'd probably be like H2 or something. Or it would actually probably go into an acid if it was done in solution. Okay. So they're just not showing that. That's not what they're showing as a product, but this is the product that you would obtain. Okay. Okay, tertiary alcohol. The tertiary alcohol doesn't have any hydrogens attached to it. Just carbons and the OH. So because I don't have another hydrogen to remove, I can't form a double bond. Okay? So I won't remove anything. No reaction. No reaction in that case for tertiary alcohols. Okay. Now, what if you want to oxidize an aldehyde or a ketone? So, alcohol will oxidize into an aldehyde or a ketone. But then what about, can you take that further? Can you oxidize it further? Okay. So that's what we're going to look at here. And then addition reactions will help us understand these things called hemiacetals and acetals. Okay? So, oxidation of aldehydes. If you oxidize an aldehyde, okay, you will pick up an OH group in place of that hydrogen. You'll get this OH. Okay? And if you have a COOH group, COOH, okay, which has this general structure to it, okay, that's what we call a carboxylic acid. That is a carboxylic acid group. So anything that has COOH or the carboxyl oxygen here with an OH on it, that would be an acid. That is an organic acid, a carboxylic acid group. Okay. So here, that's an interesting example. You know what? Let's go ahead and use the H plus instead. Yeah, be less confused. So ethanol, and use potassium permanganate here. That's an oxidizing agent in the presence of acid, and you'll get the carboxylic acid. Okay. If it's in the presence of base, then you form the conjugate base of that acid, which is the O8 anion. Okay, we'll talk about that later. But that's a strange example. But that's what it's going to go to, right? The ethanoic acid. This would be ethanoic acid, 2 carbons. It's an oic. Ic is how you end the name of an acid. And so this would be ethanoic acid, is what this would form. Okay, in that case. Okay. There are tests to identify if something is an aldehyde or a ketone. So if you have a compound, but you know it has a carboxyl carbon on it, but you don't know if it's a terminal carbon or if it's a embedded carboxyl carbon. So you can do a test, Tollens test. Okay, and Tollens test is will cause the silver ion to reduce. And when you reduce a silver ion, meaning it gains electrons. So if it's a silver ion, it's a metal. It has a vacancy for electrons, or it has a positive charge, in other words, Ag+. And if you reduce it, that means it gains electrons and goes from Ag+ to Ag. Ag is solid silver metal. Okay? And then it will precipitate as a solid silver. So, in the presence of an aldehyde, this molecule, silver ammonium complex, okay, this silver ammonium complex, which is Tollens reagent, will cause the silver of that ammonium complex to reduce into silver plus, and you'll be left with the anion of that aldehyde. Okay. All right. So that's what we call Tollens test, and you can actually silver mirror things in this way. Taking an aldehyde and using Tollens reagent, you can cause precipitation of silver to coat. Like if you had a piece of glass, you put Tollens reagent and an aldehyde like glucose over that, then it would actually coat that piece of glass with silver, and then you'd have a mirror, right? So, one way to do that. Okay, so here's an example, right? So they're testing it inside of this flask. So the addition of the reagents and the aldehyde or ketone to be tested. And then you mix it up, and a mirror coats the glass, and that would indicate that this is an aldehyde. Okay, that is an aldehyde because the aldehyde has to reduce to that carboxylic acid anion. So that means a ketone cannot do that. So a ketone cannot oxidize, I should say, cannot oxidize into that carboxylate. So as this oxidizes, this is reduced, and the silver metal will precipitate. Okay, so that's Tollin's reagent. That's the silver coating. Benedict's test will use copper. And in this case, copper is going to be reduced instead. So you take a buffered aqueous solution of copper hydroxide and sodium citrate. This is a copper 2+. Okay, it's a copper 2+ ion there. It reacts with aldehydes but not with ketones. Okay, so same idea here. You can oxidize the aldehyde, but you cannot oxidize a ketone. And so the copper will be reduced from copper 2+ to copper plus. And a solution of copper 2+ is blue. And then the color will fade as the reaction of copper plus is accomplished. And you'll see a red solid precipitate of copper oxide forming. Okay, copper 1 oxide. Okay, so that's another way. So in both of these tests, you're testing for aldehydes over ketones. So if you know you have an aldehyde or a ketone, and you want to verify which one it is, you could run one of these tests, either Tollin's test, that's the silver precipitate, or the Benedict's test, which is the copper precipitate. Okay. All right, so here they're showing that you can, glucose is actually an aldehyde molecule. Okay, it's a 6-carbon aldehyde, and so if you run this with glucose, with Benedict's test, excuse me, the copper 2+ ions will be reduced to copper 1, forming the precipitate of copper 1 oxide. Okay, and you'll be left with the carboxylic anion here on the glucose. Okay, so reduction of carbonyls. So oxidation. So if you have an aldehyde or a ketone, aldehyde in other words, if you have an aldehyde, it can oxidize into carboxylic acid. Okay, ketones cannot. They can't do that. So you can't oxidize a ketone further. So you can only take a secondary alcohol and oxidize it into a ketone, but it will not go any further. You can oxidize a primary alcohol into an aldehyde, and then you can oxidize it into a carboxylic acid. Okay? But what about going backwards? So from an aldehyde, you could reduce an aldehyde into a what? So if you oxidize, what do you oxidize in order to create an aldehyde? Primary alcohol. So it makes sense that you could reduce that aldehyde into a primary alcohol. Or that you could reduce a ketone into a secondary alcohol, right? So you can go either way. So here, with the addition of H+ and a catalyst, so this is going to require a catalyst like palladium, nickel, or lead. Okay. You can cause the reduction, meaning adding those hydrogens back. And when you add those hydrogens back, you break the double bond, right? And by breaking the double bond, you create two places where you can bind hydrogens to. Kind of like when we talked about in chapter 11, taking an alkene, break the double bond, H2, you can add that H2 back, right, and make it an alkane. Same kind of reaction here, except that the double bond's between a carbon and an oxygen. You break the double bond, you create two spots for binding, and a hydrogen goes to each one. and then you're going to form the alcohol. Okay? So these are addition reactions, okay, where you're going to break that double bond. Okay. Well, that's an addition reaction. Okay. Now, what they mean here, though, by this type of addition reaction is where you're taking taking these aldehydes and ketones and reacting them further with others so that you can form, with other OHs and things, alcohols, to form things that we call hemiacetals and then acetals. Okay? So, by addition of adding more OH groups to that carbon, which is polar because of the oxygen, you're going to create this thing called a hemiacetal, and then further you're going to cause that molecule to react into an acetal. Okay, so let's look at how that's going to be accomplished. So you have your aldehyde or ketone here, and you react it with an alcohol. Okay. You see the R group here. That R group, whatever it is, that's attached to this oxygen. Okay, you're going to lose this hydrogen. And then this group the OR group is going to get attached to the carbon of the alcohol. Okay? So, you can see here I started out with R1, R2, and now I have OR3. Is everybody following that? Where did the OR3 come from? Came from the alcohol, right? So the alcohol, the OR3, is going to attach to that carbon. Okay? And now you have what's called a hemiacetal. That's what we refer to as a hemiacetal. Okay? You're probably like, why do we ever care about hemiacetals? Well, we're going to learn later how they are biologically important, how this reaction biologically is important in organic chemistry in our bodies. Okay? All right, so you're going to form that hemiacetal, and then that can further react into an acetal with another alcohol. So once again, the OR4 is going to replace the OH that's formed when you cause the hemiacetal to form. So, okay, let's go over this again. So what's going to happen is this double bond is going to break. Okay, you're going to add a hydrogen there, but when a double bond breaks, you can always add two things, right? The first thing is you're going to add a hydrogen on the oxygen, but then here you're going to add the OR group from the alcohol. Okay, it's going to go here, and you're going to form the hemiacetal. You have 3 R groups there attached to that hemiacetal. Okay, it reacts with a second alcohol, probably the same alcohol as before, okay, because that's what you're reacting it with. And then that, once again, the OR group here is going to come attack that carbon, releasing the OH. Okay? The OH is going to be released, and in the end here, because that OH is released and it's in the presence of an acid, you're going to form some water. Okay? You're going to form H plus OH minus forms H2O. Yes?
Do the R groups have to be in that exact order? Like one to the left, one to the bottom?
No. I mean, they could be anywhere on that carbon. So, No, they don't. As long as you attach them to that carbon, that's all that matters, somewhere in that carbon. Because it's a tetrahedral molecule. You can take the tetrahedral molecule and move it all kinds of directions and orientations, unlimited, in any direction. Okay, so those R groups can be anywhere, but you have to have all 4 of them, okay, to have the acetal. Okay, so let's go ahead and look at a reaction here where we take this aldehyde, okay, we react it with methanol. So what is the OR group that's going to get added? CH3O, right? That's the group that's going to get added. So where is it going to get added? It's going to add to the carbon. Okay? When we do that, we break this bond. I'm going to form the OH. Okay? And then I'll have the OCH3 added. You guys see how that worked? Okay? That's the hemiacetal. So the hemiacetal still has an OH group on it. The acetal will not, because I'm going to replace that OH group with an OR group. In this case, an OCH3, right? Because that's what I'm reacting it with. So that hemiacetal now is going to react with another CH3OH, methanol. And I'm going to add the OCH3. The OCH3 is going to react to the carbon. And this OH group is going to leave. It's going to come off, become OH minus. And in the presence of H plus, you're going to form H2O. And now I have 2 OCH3 groups attached to that carbon of the aldehyde that I began with. Here is my first R group, and in this case, my second R group was just a hydrogen. Okay? If it was a ketone, then this would not be a hydrogen. It would be another C carbon chain. Okay? If it was a ketone, because it would have been embedded. But because it was an aldehyde, my 2 initial R groups are the CH3, CH2, and the H. Okay? R1, R2. Okay? This one? It's just going to probably become like acid, or it just, and that's another, just going to have another H plus present, and then that's what's going to react with the OH minus. Those things, they'll just be present. Okay? All right. So here is a ketone. So we have R1 and R2 as methyls. Okay? Here we're going to add an O ethyl. Okay? So for the hemiacetal, we're going to break the double bond. We're going to create the OH group. And then the O ethyl is going to get added to the carbon. Here it is. And then you still have R1 and R2. Now we have 3 R groups attached to the carbon, an OR group as well. This alcohol, the OH here, when you cause a further reaction with the ethanol, okay, that OH group is going to leave, and with H plus, you're going to form water. Okay, And then this OCH2CH3 is going to get added to that carbon. Okay? So we have OCH2CH3, OCH2CH3, CH3, CH3. Okay? So that's the difference between it being an aldehyde. With the aldehyde, you're going to have one of your R groups as a hydrogen. With the ketone, you're going to have your R groups are a carbon chain molecules. Okay? This could have been a methyl, or it could have been ethyl, or butyl, could have been a lot of things. Okay? But that's what we end up with. So that's the hemiacetal to the acetal reaction that's going to form there. Okay. Intermolecular hemiacetal formation. So this is really important to the reaction of sugars. Okay? So when we talk about glucose and things of that nature, and we show different forms that they take. So we saw that linear form of glucose as an aldehyde, right? There's a bunch of OHs on those sugar molecules. Those OHs can react to that aldehyde, and when they do that, they can become cyclic in this, okay, forming that hemiacetal. So here, for example, you have an aldehyde, and here is the alcohol OH group, okay? And the alcohol is going to react, the carbon of the alcohol, carbon 4, right, is going to react to carbon 1 here of the aldehyde, okay? And then you're going to add that this O carbon group, right? Sorry, not the carbon. The carbon's not reacting. Sorry. The O is reacting, and it's going to take with it this carbon chain. That's the R group of this oxygen. Okay? So it reacts here to that carbon, making this an OH, right? And you're going to then have the oxygen embedded into a cyclical molecule. Okay? So you see how that oxygen reacts here to the first carbon of the aldehyde, and you're going to form that chain, and then here's the OH group that came off. Okay? Now you've created that cyclical hemiacetal. Okay, so here it is in the carbohydrate glucose. So you can see glucose is an aldehyde sugar. Okay, and here is the OH group. This double bonded oxygen is going to become an OH, and then this oxygen is going to react here. Okay, you're going to lose the hydrogen that's coming off. And so you can see it better here. Here, this hydrogen's leaving. The oxygen is going here. This is breaking and becoming OH. Okay? And you will then create the bond between the oxygen and the first carbon. Okay, in that form. And now you have a cyclical 6-carbon sugar. Okay, this is often how you see glucose in its hemiacetal form. This is its hemiacetal form. Yes?
So where does that H go? You said it leaves. Right?
Well, actually, I mean, it can either go to the H pluses, or you can consider it as going right here as part of that OH. There's lots of hydrogens around because it's in an acidic situation. And so those hydrogens either become all part of the H+, or you can consider that that hydrogen right there went right there. Okay? So if that helps you follow everything, then that's fine. Okay? All right. Okay, so that's going to go there. You're going to form the cyclical molecule. Now, you'll notice that there's two actually forms that it can take. We call them alpha and beta. This is alpha glucose. This is beta glucose. Alpha is where the OH is facing down. Beta is where the OH is facing up. Okay? Because once you create a cyclical molecule, whichever way that OH is, it's stuck. It can't rotate up or down. It's stuck in either the up or the down position. Okay? So there is those two forms of that. Okay? Okay. Now, that's the hemiacetal. But then if you take those cyclical forms of the glucose molecules and you react them together, the OH with the OH. Remember, alcohol with an alcohol, you're going to form an ether, right? And in that ether reaction, here, see how it's in that ether is formed right there between the carbons from an alcohol and an alcohol. So you have the alcohol from carbon 1 and the alcohol from carbon 4 reacting. This is a 1,4 linkage between these sugar molecules. You get this 1,4 linkage here, and you form the ether. And in that process, you're releasing H2O. Okay, so you can see that the hydrogen from the blue OH and the OH here are released, forming that ether and linking those two glucose molecules together. Okay, glucose, when you link it together from a monosaccharide. Okay, so here we have galactose and glucose. Okay, so these are two monosaccharides, galactose and glucose. Okay, when they react, they can form a molecule called lactose. That's another carbohydrate. This is a disaccharide. Lactose is a disaccharide. Okay, so if you're lactose intolerant, then you can't drink what? Milk, right? Because there is lactose in the milk. So you can't drink milk if you're lactose intolerant. Okay. Sucrose, which is the table sugar that we eat, bake our cookies with, right? That's also a disaccharide. That disaccharide is glucose and fructose. Okay? Coming together in similar ways. Okay? Now, when it's in this form, in that disaccharide form, you created that linkage. Linkage. Okay. Tautomerization is the process where if you have a carboxyl group, okay. Well, come back. Okay, in the ketone form, we call that the keto form. So here's the keto form. Then it can actually, that double bond can move into the enol, ol for alcohol. Okay, so to the enol form from the keto form, and that's called tautomerization, and that's the keto-enol tautomers. Okay, so that double bond can go between the carbons instead, and when it does, this hydrogen has to move, and so it goes over here to the OH, and you can get you see this double arrow. That means what? Okay, it's reversible, so and there's an equilibrium that's established between the two, so they actually pretty much exist in both forms. Okay, It's just going back and forth between those. Now, one of them might be in a higher existence, like the keto form might be the one that exists more readily. So the eno form is in low concentrations, where the keto form is in high concentrations in the equilibrium that's established. Okay. The keto form is usually more stable, so it has a higher existence. Once going through that. Okay, so here is a reaction summary. Okay. Preparation of aldehydes and ketones will be through primary alcohols or secondary alcohols, not tertiary. Okay. Aldehydes and ketones oxidation. Aldehydes are oxidized to carboxylic acid. Ketones are oxidized not at all. Okay, so you don't get any product from that. You can determine whether something is an aldehyde or a ketone through Tollens or Benedict's tests. Okay, reduction. Remember, if you're an aldehyde, you will reduce to a what? Primary alcohol. If you're a ketone, you will reduce to a secondary alcohol. Okay? If you take a ketone or an aldehyde and react it with an alcohol, one alcohol, what are you going to form? Hemiacetal. You react it with two alcohols and you will form a acetal. Okay? So you'll form the hemiacetal and then the acetal if it's two alcohols. All right? Aldehydes and ketones can exist in keto and eno forms. Okay, so let's look at a few of these, right? Oxidation of an aldehyde to a carboxylic acid. Reduction of aldehydes or ketones to the alcohol, primary or secondary. Make sure you're specific a lot of times. So if a question asks, if you have an aldehyde, what is it going to reduce to? Don't just say an alcohol. Say a primary alcohol. Be specific about that. A ketone is going to reduce into a secondary alcohol. Okay? So here we have aldehydes and ketones reacting with an alcohol, which will form a hemiacetal. And then, if it reacts with a second alcohol, it will form the acetal plus water. So H2O will be a product of that final reaction as well. Okay. Here's keto-eno isomerization, tautomerization. I'm sorry, not isomerization. Okay, so let's go ahead and practice. Okay. Please name that. It's not an alcohol. And if it was an alcohol, there's a different name that you would use. But you're right about what type of molecule it is here. Start there. What is that? It's a benzene, right? You recognize it now? Okay, that's a benzene. Okay, so that should help. That's part of the name. What's that? It's an aldehyde. It's creative. Not the name, but it's... So benzene aldehyde, we're going to call that benzaldehyde. Okay? Right. The name is benzaldehyde. So instead of having the ene, you're going to have aldehyde. Benzene, drop the ene, call it a benzaldehyde. Okay? So that's a benzaldehyde. If I put something onto the benzaldehyde like that, now what would I call it? Well, that's a methyl. Okay? What's the name of this then? 2-methyl benzaldehyde. 2-methyl benzaldehyde. Okay? Is there another way instead of using numbering, could I use a letter? If I can, what letter would I use? On a benzene, okay, M is right here. Para is right here, P. Not you. O. O.
O is 1 and 2.
Ortho. What?
O is 1 and 2, right?
That's right. Okay, so that's O. O-methyl benzaldehyde. Okay? Okay, or 2-methyl benzaldehyde. If that was the case. Okay, I want 2 names for this one. I want the IUPAC, and I want the common name. So there's no side groups on it. It's just straight out what's the name of that molecule. Okay, that's one of them. Good. Yeah? It's one. Now do you know the common name? You get the common name. The common name for a 2-carbon aldehyde. You can't think of common names. Start with the IUPAC name. What's the name of something that has a 2-carbon aldehyde? Yes. Good. Yes. That would be if it was an alkene, but this is an aldehyde, so the ending for an aldehyde is what? Not -ene. Good. That's the first name. Okay, that's both of them. So it's a 2-carbon, not a 4. 2-carbon. So if it was 4 carbons, that was a butanol, then that would work. Good. That's for this 2-carbon aldehyde. Now, think about what the common name would be. Okay, so here they are. We have ethanal, and we have acetaldehyde. Okay? You guys know what acetic acid is? Acetic acid is vinegar, and acetic acid is a 2-carbon acid. So here's your aldehyde. Okay. That can oxidize into acetic acid. Okay? Acetic acid or ethanoic acid if it was a 2-carbon acid. Ic acid, that's how we always have ic acids here. Acetic acid, ethanoic acid from the ethanal or the acetaldehyde. We'll go to acetic acid. Okay? What's this? It also has 2 names. No. Just name it as a 3-carbon aldehyde. I can see why you want to do iso, but it's not. Okay, that's one of the names, except you don't have to specify the location. Why? Okay. Okay. There's another name. It's a more common one. Good. Good. That would be for 5. And that's an aldehyde. That would be a 3-carbon aldehyde. The ending for a ketone is different. Okay? Not spelled exactly right, but I get it. Good, that's the other one. Okay. That's bus. You don't have to say ketone. But if you do the common one, this is the simplest ketone there is. And it's probably the one that you're most familiar with at your grocery store. Okay? If you go to the makeup aisle, you're going to find this stuff. Okay, so we have propanone, okay, which is also acetone, okay. All right. Okay. Let's name this. That's just two ways to look at it. It's the same molecule. Okay, OL would indicate what type of molecule? Yes. So that's wrong. Because that would mean this is an alcohol. It's not. Okay, you're super close. Where is this? Because it could be here, it could be here. Yeah. Sorry, let me see. There we go. Great. Ene would be a double bonded carbon. This is a carboxyl. Good. Oh, I'm sorry. You put al. It's not an al. It's not an aldehyde. Good. Now this would be an aldehyde if this was an H, but it's not. That's not an H. That's a carbon. That's a CH3. Okay? There we go. Okay. OL means alcohol. It's not an alcohol. Okay, so the ending for a ketone is O-N-E. One. I'm sorry, I didn't see your guys', but I was talking to stuff. Good. You're right. Let me see. Yes. There you go. Yes. Yes. Okay, so this is a 4-methyl-2-heptanone, right? One. No. How about this one? Everything's right except for the fact that you write 4, 6.
Oh,
2. Okay, once again, it's not an alcohol. What's the ending? What's the ending of a ketone? It's not a methyl. But you're on the right track. There we go. Yes. Yes. Okay, how many ethyls? Is there just one? Good. Octanone. Okay, there's more than one ethyl, and it's ethyl. Okay, that's good. 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 Okay, so I have 2 ethyl groups, right? 1, 2, 3, 4, 5, 6. 4, 6 diethyl. Okay, 4, 6 diethyl. 1, 2, 3. It's an 8-carbon molecule. Octanone. Okay, octanone. 4, 6 diethyl, 3 octanone. Yes.
You can give us the line that have to bring up
Are you saying from this?
how did it get to know it's gonna?
Okay, 1, 2, 3, 4, 5, 6, and then let's see where to go. You have, so it's saying there's 2 CH3, 7, 8. One of them's going this way, and one of them's part of the chain. Okay. So they're saying on that carbon you have an ethyl there and an ethyl there, but one of them has to be part of the chain.
So said first 1, 2, 3, 4.
1, 2, 3, 4, 5, 6. Because this one is coming off of here, right?
Yeah.
Go away. Okay.
That's the branch.
Whoops. That's the branch, right? And here you have a branch here and a branch here. But it's going to be 6, 7, 8 as part of the branch, and then the other one is coming off. See that? Does that make sense? If you had something like this, you would just want to draw it out to make sure you have it, and then count it. I don't do this a whole lot. I don't really do that. I would mostly just give you something like that. Okay. But I mean, it is expected that you would be able to recognize that.
Sometimes the carbon going to the branch, and still you could have counted for kind of the longest chain. So you didn't have a diagram like this.
So it might have been easier if they would have just said CH2, CH3, CH2, CH3, right? Because then you would say, oh, that's part of it. Is that what you're saying?
I guess.
Yeah. So instead of having a 2 there, just put it in parentheses. Say there's just 1 there.
Yeah, that's good.
Yeah. Right. Then you would recognize it.
Yes.
Okay. All right. Okay, that's it for today, guys. We're gonna pause there.